Should we start now? Cool. Hello, everyone, and welcome to the afternoon session of Data Carpentry, where we're going to be talking to you about data analysis using Python. In particular, we're going to be focusing mainly on data frames, which are a class of object that is, I think, as they mentioned last session, one of the most popular packages used in Python nowadays, just because of how easy it makes working with large data sets and large CSV and TSV files. So, I mean, they were just going to learn what data frames are, how to manipulate them, how to work with them, et cetera, et cetera. So, to start off, I'm going to introduce myself. I am Francis Nguyen. I am a second-year master's student in medical biophysics. I like helping out at these data carpentry events. This is my second data carpentry, the third carpentry teaching session. So, welcome. Sorry if I'm a bit slow or stuttering. I just had like 3 cups of coffee. Anything else good? Sweet. So let's get started. So normally to work with to work with spreadsheets and such, you might have to go through some clunky. So I wasn't here for the opening session, but you might have to go through some clunky programs such as Excel, where it loads up everything, it uses a lot of memory, and everything's very visual. You have to. I don't have a license for Excel. Okay. Another bad thing about Excel is you need a license for it. If you don't have it, you can't use it. But the main point that I'm trying to get across is that it's all very point and click, and that's not always the best way to go about using things, especially if you want to go and perform one operation to a bunch of different data sets. Going through Excel, having to go through and click on each and every item is an absolute pain. And so we're going to work through how to manipulate these data objects or data frames in a more programmatic way, so that you write once, execute on a whole bunch of different files, and everything is absolutely a lot easier and a lot faster in order to do such things. But first, we're going to go through, and I think this was talked about slightly during the last presentation, but we'll touch on it again, the concept of packages. So packages are, you can think of them basically as large repositories of code that other people have written for some specific purpose, and they are generally made free and available and usable by everybody. So the normal way of getting at one of these packages, so there are a ton of things that you can do with Python, and there are a ton of packages. As a result, it is a bit infeasible for them to make it all available right at the start, because that would require a lot of memory. So instead, we're going to start off by using the import command, which tells us to load up a particular package into Python. In particular, this import numpy statement, import tells me I'm going to load up a Python package, and numpy is the name of a particular Python package that makes it really easy to do math on large data sets at once. And just as a proof of concept, we're going to tell it to take the mean. Oh, shoot. Side effect of coffee. You can't type it. We're going to tell it to take the mean out of these 5 numbers. So just breaking this down slightly, mean is the name of some function which calculates the mean of a bunch of numbers. It's inside of numpy, so I go numpy.mean. And then inside of it, I use circle braces in order to tell it that I'm going to call on this mean function. And as we saw last lesson, these square brackets allow us to give it a list of numbers, or like a sequence of numbers. And you can tell it output the number 3, and that's because the mean of 1, 2, 3, 4, and 5 is 3. To get more info about any one of these particular functions, you can always just go up to the .mean, and then you can get something called shift tab. So if you do shift, then tab, you'll get this information over here, which is, it describes the signature, which tells you how to call it. So in this case, we've got numpy.mean. It takes a, and at first glance, not actually clear what a is. If you scroll down, there's a list here, parameters. And you can see that a is an array-like, where array-like means any sort of object that contains a whole bunch, like a sequence of numbers. And in this case, as before, we had given it a list. Oftentimes, it is not oftentimes you don't feel like writing out the entire package every time. And what you'll see a lot of people do, especially for NumPy, which is used almost everywhere, is to just import NumPy as NP. And from then on, instead of calling it numpy.mean, we can just use np.mean. And this sort of nickname, in the back end, calling numpy.mean, but this sort of nickname allows us to save on a lot of typing. Yeah. Now, I've only covered NumPy so far, and I think last lesson you discussed Seaborn, but there are tons of packages in Python which aren't included by default. And so to get at the rest of them, I'm just going to open up the Anaconda prompt. Cool. I'm going to type in Anaconda. Sorry, is this legible from back? Awesome. Let's say I want to search for a package called natsort, which allows us to sort natural numbers. In this case, I enter in our command Anaconda search. -tconda just tells it where to search or what repository to search in, which in this case we're telling it to search through Conda, and we're asking it to find all of the packages that are called natsort. And you can see through this incredibly broken table, this is normally supposed to be like a table. These bars are supposed to line up, but this command prompt window is not large enough to hold the entire table, so it sort of breaks apart at some points. But yeah, you can see it comes up with a bunch of results for different packages, all of which implement this natsort thing to sort lists naturally. If you then want to install it, Anaconda, sorry, Conda install natsort. You can see that it's going to automatically figure out how to install it, because often these packages will depend on other packages that have to be installed beforehand. But that's all covered by Conda. It'll automatically install everything for you, all the requisites, figure out exactly how to install it. And it's like, oh, in order to install natsort, you must also install CA certificates, certify, Conda, OpenSSL. I have Conda. What are you talking about? Now, hit yes for it to proceed. You wait 10 seconds for the internet to download. And then it'll have it installed. Now, personally, installing things via the prompt is a bit of a pain. So if you like to go through graphical user interfaces, you can always, sorry, I went through that a bit fast. You can always find the Anaconda Navigator app, open that up, give it 10 seconds to run on this laptop. I'm willing to bet your computers will be a lot faster than mine. Here we go. And we can see all the applications that are currently installed. Go to environments, and I go to all. We can, sorry, so environments on the left. You click on this thing over here. I'm sorry, I can't make this larger, but this is an incredible page. You switch it from install to all. You can search for a package. Let's say, well, let's do natsort again. And if this wasn't installed, you could just click on that and then install it, which is really easy. You just hit apply, and then it'll automatically do the same thing that we saw in the command line. Sorry, any questions?
So where do we find the packages that are available based on function? If I want to find something that calculates linear regression, for example.
Usually I just Google for packages or for like Python stuff that does linear regressions. Apparently this also has a search function where you can see this. It does something like this where it learn sparse linear models. Normally though, I just Google it. And you can see that the very first couple of results all just tell me to install scikit-learn. It's also installable. Okay, so in order to actually get into the meat of this lesson, where we're actually going to do all of the data analysis, we're going to have to download a data set which has been prepared especially for this workshop. And just a little bit of the background as to what it is. Let's go through here. Here we go. We are going to go through a longitudinal, Longitudinal study of the species abundance in the Chihuahuan Desert ecosystem near Portal, Arizona, USA. This study includes observation of plants, ants, and rodents from 1977 to 2002 and has been used in over 100 publications. There's kind of information available in this abstract. Sorry, does everyone know how to get to the GitHub? Where we have all the time? Awesome. There are several data sets available related to the study, and we're going to be working with some pre-processed data sets so that it's all easier to learn from. It's all available on the website. And in particular, we're going to be using a comma-separated value file, of which I have open. Voila. The file that we'll be working with looks a little bit like this. You can see it's a comma-separated file, so you can think of this as a table. The data points inside of the table are all separated by these commas that are everywhere. Numbers show up as numbers, but any sort of string or any sort of contiguous bit of text is covered by these quotation marks. And we can also tell that this file is enormous at 34,000 lines, and it's got a header at the top, which is to say it's got this line at the top which tells it exactly what all the data points mean in the rows below it. So it includes things like an ID, a month, day, year, ID, et cetera, et cetera. So in order to read this, we are going to use a function called read CSV, and we are also going to need to import pandas. Import pandas as p, and this sort of import pandas, but give it the nickname pd. And the result of that is you don't get any sort of result from that. There's no real output from an import command, so you don't really see anything, but you can tell at the left, since it is no longer returned, it's got a number inside of it that it ran successfully. So pandas can read CSV files saved either on the computer or directly from a URL. So in this case, I'm just going to go surveys pd dot read underscore CSV, and we have a giant URL, which I'm actually just going to go into the Etherpad, whose URL is over there, but I can just type it in anyway, softwarecarpentry.org/2018-07-12-U Toronto. Near the bottom, we can see there's a URL, so we're just going to copy and paste this URL rather than trying to type it out, because it's a lot easier to do that. Paste that in there. Make sure that it is between the two quotation marks. Make sure that you remember to put an ending open brace. And what's going to happen next is it's going to take a while. So it's a large file, and it's going to take quite a while to download off of the Wi-Fi that we are currently using. But in a couple of seconds, in a minute, we'll see this over here turn into a number, and that means that it's completed successfully. Oh, right, sorry. pd.read underscore CSV. Sorry about that. I'm actually going to close the inspector. Oh, yeah. If anyone's having problems downloading it, we have it on the surveys space equals space pd.read underscore CSV. If you have your what, sorry? You would give it the path to the thing. So it could be something like C:/documents/ wherever it's located. I guess put up your yellow sticky if you're having problems, and your blue sticky if you're A-okay to go. If you're missing a sticky, please flag a helper. So I guess blue if you're able to load it and you're seeing this number over here, and yellow if you're having any sort of issues whatsoever. And I guess if you want to verify that it loaded correctly, just type in the name of the variable that we saved all this data to, surveys, and execute that line of code, and you'll see all of the wonderful data, all 35,000 rows loaded into your Python notebook. And so I guess blue if you got that, yellow if you don't. Thank everyone. Yes.
So when we just did that, is the data actually part of the notebook now or not?
I mean, it's saved in the interpreter, but it's not saved in the notebook. So if I were to close Jupyter and close down my Python, when I load it up again, surveys would no longer be filled. I'd have to rerun this line.
So is this in Jupyter where it says run, it would run everything I have on that notebook?
There's multiple runs. So there's run selected and there's also run all. And there's also restart kernel, which means clear everything, pretend we had closed Python, and then run everything from the start. Give everyone a little bit more time. I guess if you're finished, take a look, see what you notice about the data. Yes, it means not a number, but if you check the actual raw file, there are certain cases where there's just no data. And so it's using these nans as missing data. And that is an important detail. And it's something that you're going to uncover a lot if you work in data science. Oftentimes fields will just not be filled out. Data will be censored either because somebody forgot to write it down or because they thought they wrote it down and Excel messed it up. All of which can happen. In any case, other cool stuff is it's really hard to see on this laptop, but it's actually doing this sort of zebra striping where it's light, dark, light, dark, light, dark. And that just helps us see the data a little bit better. Across the top, we can see all of the different column names, which were conveniently taken from the header line of our CSV file. And we can see on the left over here, the row index, which is essentially the row that something is placed on. And so I think almost everybody is done. So I'm just going to move on a bit. Next command that we are probably going to want to learn is head. And the reason why is going to be really apparent. Head just grabs the first couple of rows from the data frame. So in this case, it grabbed the first 5. You'll notice it grabbed the first 5, and the last column is numbered 4. Sorry, the last row is numbered 4. And that's because Python and almost every programming language will index starting from 0. Questions? I can totally, like this. Awesome, sorry about that. So surveys.head, it automatically grabs the 5 rows. And this number isn't 5 because it starts indexing all the way from 0. Okay. The next thing that we're going to learn is the type command. And the name of this, type surveys. And what type does is it tells us like basically the type of variable that is located inside of surveys, which is where we save the CSV file to. And we can see that it is of type pandas.core.frame.dataframe. Which just tells us that it's loaded from pandas, essentially. And if you just do if you just do, I think it's surveys shift tab, Jupyter will automatically bring up this nice little information about what surveys is, including, of course, its type as a data frame, all of its different not all of the columns, but the first couple of columns, and just more information about what data frames are in general. So shift tab, autocomplete, and it's really helpful, especially to avoid typos. In any case, let's continue forwards with the surveys.info command. Surveys.info command gives us a lot of information, even more information about the data frame, but this time it gives us some important info that was missed during the first couple of information gathering commands. Notably, this tells us the number of entries, which is corresponding to the number of rows that are inside of the data. It tells us all of the columns, and it tells us the type of the column at the far right, which tells me that the record ID, month, day, and year are all integers of 64 bits. Hindfoot length and weight are both floats, which are floating point numbers, which is basically a decimal number. And then the rest are objects, which in this case we're just going to consider as being like strings. Sex, for instance, is only ever male, female, or not a number for missing data from this analysis. And like we've got the genus, the species, the taxa. We can see its memory usage in RAM over here. Just a quick segue into the different types of data that is available from, I'm just going to scroll. Just a quick look at the different types of data that we might see. There are a variety of different data types that we normally come across. We've got we've got nominal variables, which have discrete labels. We have ordinals, which are the same as nominal, but we have some order to it. We've got binary variables, where it's only ever true or false. And we also have both discrete and continuous numerical variables, such as ints, which, as I described, are just ever whole numbers, and the continuous number float for floating point, which is any sort of decimal number. So this, if you're ever wondering what sort of variable you should expect something to be, this graph is pretty useful, or this table. So next thing that we're going to go through are a couple of other information gathering techniques regarding surveys. So first off, we've got surveys.shape, which tells us in a more succinct way, the number of rows and columns that are inside surveys. You'll notice that this is inside of circle brackets, which represents it being a tuple. And with all tuples, we can index into them. So I can grab .shape and then use the square brackets to subset into the tuple. And I just grab the first one, which is the 0th one. And we can see that I grabbed the number 34,786. And we can do the exact same thing. I'm just going to copy and paste that to grab the number of columns, .shape at 1. We've seen head already, which grabs us the first couple of lines. But we also have something called the tail, which, drum roll, grabs us the last couple of lines. We can grab the names of the columns. Am I going too fast, or is everyone able to keep up? Cool. Surveys.columns, which I could bring this slightly larger so we can see more than one thing at a time. Oh, we can, sweet. Columns, which gives us the different column names. An index, which gives us the entire, all of the different row indices. You'll notice that it didn't display all 0 to 34,786, and that's because internally it's just telling itself they start at 0, they stop at 34,786, and they go up by 1. And that's how it's storing it internally. We have seen surveys.info. Which is something we've already seen. Yes, sorry, question.
Is there some commands we need to put like the parentheses
So the parentheses, it's a bit of a technical thing. The parentheses tells it that there is some code that is run in the background, whereas if you index into it without the parentheses, it's just some number that it has already ready. So the index is already stored as part of the surveys object, and you can retrieve that at any time without it having to run any code in the background. This is almost a guarantee that there's no code running in the background. But as for which ones have parentheses and which ones don't, it's something you'll eventually get a feel for, but for now it's just an implementation detail inside of how it. So we've got .info with parentheses. We've got surveys.describe. The describe one is my personal favorite because it grabs only the numerical variables, and it gives me things like how many of them were there, what were the means, standard deviations, the minimums, the percentiles, the maximums. And for some of these, obviously, the mean day doesn't really mean a whole lot, but oftentimes you'll get like, oh, I wonder what the mean weight of my entire data set is. And it's right here, easy enough to access. So that's surveys.describe. I forgot to mention one really important detail, which is these numbers over here. So you'll notice it says 34,786 non-null. Non-null in this case means that there's actual data inside of it. For certain rows, there was no sex, for instance, and so that's why we might see that there are less sex objects than there are in the species ID objects, or in the less hind foot lengths than there are rows in the data set. And it's just because for some of them, it had no value. Yep. Only the numerical data, I'm afraid. Okay. So without any further ado, let's move on to the first challenge, of which I'm going to sit down and type out. Based on the output of surveys.info, can you answer the following? What is the class object of the object surveys? How many rows and how many columns? Is there not the same number of rows, observations for each column? So I'm just going to, sorry about that, ask that everyone run surveys.info on their own. And I guess, first off, take your blue stickies and put them down. And second off, talk to the person next to you and see if you can answer all 3 questions. And then once you've come across, or once you think you figured it out, put your blue sticky up, and then I'll call on somebody again to explain. Does anyone want to volunteer to answer the very first question? Yes. It is, in fact, a data frame. The full path to which is over here. There are some types that aren't classes. I think it's mostly like, so you can say like 3 as a type and it's of type integer. Not every type is a class, but oftentimes the type will be a class, and these class objects are generally more complex. So that there's the concept of like base classes, stuff like integer, stuff like booleans, which are built into Python. And then there's classes, which are built by other people that have a large amount of code running in the background for them. And these classes are generally more complex. That being said, classes are a type of type, if that makes sense. They're both the type. It's just the fact that when you do, so let's say type surveys, like this data type is part of this package, the package being pandas.coordinateframe.
Data frame is
Essentially, yeah. There are other classes which can also contain tables, but for now, the only tables that we'll be working with will be contained within these data frames. So with that in mind, does anyone want to take a stab at the second question? How many rows and how many columns? And where do we find that from within this info doc? Raise your hand. Yes. Yeah. Right. Cool. And can somebody tell me why all of these numbers are not the same? Real quick. Anybody? Everybody? Right. Inside of the actual CSV file, we've got things where the size isn't filled out or 9-foot length isn't filled out, et cetera, et cetera. Cool. That's great. Right now you might have noticed that downloading the data set took absolutely forever, and we might want to save it locally in order to avoid having to download it again, or say we had performed some calculations on it and we wanted to save those calculations. The way to do that is via this handy command called surveys.to_CSV. You can also just do to_CSV. There we go. And it gives us the full signature. In this case, I'm just going to save it to something called surveys.csv. And I'm going to execute this. And once it finishes, it is now saved in the computer. For me, since I'm a Windows machine, it's actually saved into my home directory. So for you Windows users out there, I'll just go into my home directory. Users. Surveys.csv. If I zoomed in. But yeah, you can see that it saved itself inside of my home directory, and that's where it's currently located. I can then load it up using the exact same command that we had earlier, pandas.read_CSV. Tab. You can see that it takes a file path. Right, I can give you that. Surveys.csv. And now, since it's already been saved, I can load it, and it reads. And if I wanted to just make sure that it loaded properly, just look at the head. Whoa, it's grabbed all of these. That's great. I did, however, completely neglect to say something, and that's that under the to_CSV file, we actually want to turn off something called the index, and that's because ordinarily the CSV file ordinarily doesn't have the row numbers in it, and when Pandas tries to save a CSV, it'll try to insert them. So we're going to use index equals false, and that'll, after I rerun these commands, you'll notice before I had this unnamed 0 column over here, which is like, it found a column, it wasn't quite sure what it represented, so I just removed the row index. Now when I look at it, hello? Pretty sure that was supposed to remove that. Oh, haha, that's because I overwrote my thing. 1 second. I'm going to go all the way back up and re-download this data set because I messed up. Sorry, guys. And then I'm going to save it and reload it. There we go. So now in this uncorrupted version, we can see it's regenerated the row names, but now there's no ghost column with all the row numbers in it, which is useful. So up until this point, every time we've taken a look at surveys, we've tried to grab all of the columns at once. That's often the case not exactly what you want to do. So we're going to subset these data frames in order to grab certain bits of data from them. In this case, we take surveys. We use the square brackets, which allow us to index or subset inside of the data frame. And using this, we're going to give it one of these column names. For instance, let's say species underscore ID. If I just run this, it's going to give me all of the different species IDs, and I don't really want to see all of that, so I'll just take the first 5 using head. And we can see that it's grabbed the first 5 species, and we can verify that that is, in fact, the first 5 species. That's great. Let me verify it again. I'm just going to copy and paste that. And let's look at something that actually changes. Record underscore ID. Whoa, it grabbed 172, 224, 266, 349. And if I scroll up a bit, you can see, yeah, I did in fact grab 172, 224, 266, 349. So that's great. We were in fact able to grab the record ID. You'll notice that inside of here, it doesn't display the surveys, or sorry, the column names anymore, because there's only really one column to display here. Yes. Nope.
Is there a way to get like all the unique values? Like when you did species, I just want to see.
We'll be getting to that later.
Perfect. Thank you.
Just in a bit. For now, let's just go through the different ways of subsetting it, and then we'll go into how to do unique stuff. The other way of subsetting, besides using these square brackets, is to use the dot notation. So surveys dot record underscore, and we can use tab completion. So if I just type enough that it's uniquely identifiable, and then I hit the tab key, it'll automatically complete it, which is great for jittery and want to make sure that you don't do any typing errors. Dot head, yeah, it's the exact same thing. That being said, we won't be using the dot notation very often because it's often recommended that you use the bracket notation. Another reason why you might want to use the bracket notation is that it actually lets you do more than one column at a time. So firstly, let me just break this down real quick. I've got square brackets. I'm going to let it know that I'm subsetting. I'm going to actually do another set of square brackets. And this is, as you might remember, it lets you create a list. And in this case, I'm going to give it a list of different column names that I want to grab. So species underscore ID and record underscore ID. And as before, I'm only interested in seeing a couple at a time, so I'm going to use the dot head. So to break down exactly what this did, the first brackets, I forget if this was covered or not, but this number sign lets me write out a comment. So later, when I look at this notebook, I know exactly what I was trying to do. The first brackets tell me to subset. Second brackets list of column names. So as you can see, this time, because there are 2 columns that I have subsetted, it preserves the name of the columns, species ID and record ID, and just around 5 columns, which are this 0 through 1, 2, 3, and 4. You might have also noticed that the IPython notebook has, beyond just not displaying the column names, it's actually displaying the numbers as like completely differently. Over here, it's in this weird like console text, and it gives me all of the different information about like the data type. And this one just sort of elides all that information. If we wanted to figure out exactly why that's happening, I'm going to copy and paste this code. And I'm going to surround it inside of this type command. So type surveys.record underscore ID.head. And in this case, it's actually of a different type. It's no longer a data frame because it no longer has multiple columns. It's using some Panda's internal thing called a series, which is like a data frame, but it only has like 1 column. And it's technically 1-dimensional as well, whereas data frames are usually always 2-dimensional. Just to really bring home my point, actually, sorry, started typing that. I Let's just copy and paste. I'm going to go up here. I'm going to grab this part. I'm going to stick that inside a type. And you'll see, because I gave it 2 columns to use, it has kept the data type constant as a data frame. A lot of the techniques that we will be covering in a minute will apply to both series and data frames. Now then, sorry, are there any questions about all this? Yeah, keep going. Cool. So there is more than one way to subset our data. So far we have done the bracket notation. Now we're going to learn your .look, which is, so the bracket notation is actually a bit of a shortcut to this loc command, and we can call loc rather explicitly just using .loc. And the reason why we might want to do this is that using the .loc notation, we can actually grab more than one dimension at a time. So let's say I go 0, 2, and 4. The first argument to lock, you're using square brackets, you give it a list corresponding to the rows. You do comma, and you give it another list corresponding to the columns. And we can see it has grabbed from rows 0, 2, and 4, the species ID and the record ID. You'll notice that it didn't quite fix the row, sorry, like it kept the row numbers at the left over here. So we know this came from something where the rows were 0, 2, and 4. Fun fact, this loc is actually a command, but for whatever reason, like normally with commands and methods, you would have to use circle brackets. In this case, they've done some fun hackery to use square brackets instead, which allows us to subset through surveys as though we're just using the normal bracket. We can also just give it a single number rather than complicating our lives with many. Let's say I just wanted to grab the very first species record ID. And we can see it actually just gave us a single number. And if I type this, using the type command, it has reduced it to its most simple form. It's no longer a data frame because it's not 2-dimensional. It's no longer even a series because it's not really 1-dimensional either. It's just a single value. So it has automatically given us the base integer type of 1. If using the .loc command, we leave out the columns. So in this case, I'm just going to, these spaces aren't technically necessary. If we leave out the columns, it'll automatically grab all of the columns. Grab all of the columns. If we want to select all of the rows, but only a couple of columns, we unfortunately cannot just, so normally it's rows, then comma, then columns, but you can't leave a blank space like this. So pandas will expect us to use a colon operator if we want to select all rows. Sorry, put a little, all rows. And in this case, I'm going to grab, let's say, the record ID and the day. And let's just grab the head. Yeah. And so here I've told it to grab all of the rows, but only the 2 columns, record ID and day, and I've used the dot head in order to just shorten it down to the top 5. Actually, there is a better thing that I could have done here. That is dot shape. And if you recall, dot shape tells us the number of rows and columns. So in this case, we can verify that this colon operator has expanded out to be all 34,000 rows, almost 35,000 rows, and the two columns we were interested in. That being said, sometimes this is really annoying to have to specify in advance all of the, like to know exactly what all the names of the columns are. That's right, that's the next section. So we can do something called slicing, where I can grab, let's say I want to grab the 2:4, which represents 2 to 4, so rows 2, 3, and 4. And I'm going to grab everything from the record underscore ID to the day. Cool. And as you can see, it's grabbed rows 2, 3, and 4. By this 2 to 4 thing, it's like, oh yeah, you want to call it rows 2 to 4, and you wanted columns record ID to day. So it's grabbed the record ID, the month and day. Yes. Mm-hmm. Mm-hmm. Why is it shown? So if you have 2 to 4, it would show 2, 3, but not 4. In this case, in the .loc notation, it's special in that it will include the end index. I will show you right next the version which won't grab the fourth one as well. The .loc is special in that regard. Good eye. Question. In this case, it's interchangeable. I can do single quotation mark. Whoa! I can do single quotation marks or double quotation marks. The only thing that you have to be careful with is you have to be consistent. Consistent being like on both sides, it has to both either be single quotation marks or double quotation marks. And I don't think Python differentiates between the two at all. Well, it could be, yeah. Another question. Any other questions? Cool. Okay, so I'm going to prove that that's, yeah. Next thing that we're going to do is surveys. So oftentimes, even using this notation is too tiring. I don't know what the columns are in my data set, and sometimes I don't really care. Well, I should care, but yeah. So I'm going to use the iloc command for, I think it's like index locator. And what that allows us to do is it allows us to grab things instead of by the label at the left or the label of the column at the top. I can just refer to them by their number, like the first column, second, third. And you can see it's the same output. It did the same thing in this case. But instead of referring to the columns by name, I've referred to them by column. You know what? Let me just prove that. Yeah. And in this case, to your point, 2 to 4 in the integer locator command, it recognizes not to put the last index because that is the default way that it handles this slice notation. Ooh, 3. There we go. In this particular case, the row indices are equal to the actual position inside of like their number position. So you might have noticed that going 2, 3, and 4 and 2, 3, and 4 up here refer to the exact same rows. But there are some cases where you might have row names. And in this case, it is much more convenient to use iloc and use the numbers rather than trying to look up what the names of the rows were in the first place. iloc gives you, it lets you index by number. So column number 0, column number 1, column number 2. Under loc, I had to know exactly what it was called, the full string name. And in this case, for the rows are numbers, so this didn't matter at all. But in some cases, you may come across a data set where the rows are not numbers. Personally, I prefer to just ignore everything and use iloc. But you can refer to the row numbers, sorry, the row names if they're strings, use them loc instead. One final bit of slicing is it is often the most common operator that everyone uses is to just figure out what the first 5 rows are, or the first couple rows are, or like some index of rows. And so the brackets without the loc will automatically give you, let's say I go from 2 to 5, it'll automatically grab me the rows, even though I didn't really specify what columns to grab. It grabbed all of the columns for those rows. Grab all of the columns. Everyone cool? Great. I'm going to ask everyone to put their blue stickies down, and we're going to do another challenge. Today's challenge is track the 200th and 201st row of the surveys data set and assign the resulting data frame to a new variable name, which we're going to call surveys underscore 200 underscore 201. Remember, Python indexing starts at 0. Second part, can you get the same result from surveys.head using row slices instead of the head? All right, let's put it low to the ground. There we go. The third question is, there are at least 3 distinct ways to extract the last row of the data frame. How many can you come up with? Good plan. Oh, work with the person beside you. Put up your blue sticky if you're done, your yellow sticky if you ever run into any sort of issues or would like any help. And then at the end, I'll ask someone to, I guess, come up and type the code. Cool. Good luck. One really quick tip that I completely forgot, but is in my notes. If you give a number to head or to tail, you'll notice if I hit shift tab, the signature says n equals 5, and it's like return the last n rows. So if you change n, if you give it some number, it affects how many rows it gives you back. Works as well. All right, it is now 2:20. So can I get volunteers from the audience to answer questions 1 and 2? You can have a tiebreaker today.
You're going to tell you?
No, either one fine.
Okay. I think for this one, I can just put in.
Put it into surveys underscore 200.
Yeah. So for the 200th row, we want row 199.
Right. That's because they start off from 0. So front of row is actually index 199.
And then it should go up. We want, I think, still 201 because it's exclusive.
Cool. And now can you assign that into a variable surveys underscore 200 underscore 201?
Yeah. 200.
You'll see there's no output, but if we just type in the name. Perfect. So thank you very much. And can I ask you to do the second question? Awesome. So how can we get the same result from using surveys.head using row slices instead of the head method?
I think that you just go from 0 to 5. How do I go down? Oh, I have to go up. Yes?
Yes. Yeah.
Yay!
Great. Awesome. Thank you very much.
You're welcome.
Thank you. Round of applause for our two volunteers. All right, and on the very last question, there are at least 3 distinct ways to extract the last row of a data frame. Does somebody just want to raise their hand and tell me what ways you guys have found? Yes. Yep. Yep. Mhm. Yep. Times 1? Yeah. Awesome. That gives us record number 30,986, which, if we go to the thing, if we go to the actual file, we can see, yep, the very last record has record ID 30986. Cool. Somebody want to volunteer a second method that they discovered? Yes. Cool. In this case, I'm not entirely, you don't necessarily need the second one, but I guess if you do, it preserves the data frame. But yes, that works as well. Third method? Oops. Yep. Is it IDX or INDX? Oh, sorry. You mean like 34,786? No. Yeah. Oh, cool. Awesome. Cool. Nice. I had no idea that existed. Neat. Last underscore valid underscore index. Cool. Interesting. Sorry, and as before, if you ever want to figure out how something works, you can hit Shift Tab, and it'll pull up this little menu, this little info box, and last underscore valid underscore index returns the index for the last non-null value. Cool. No idea. Interesting. My personal favorite method is to just do .iloc at -1, which gives you the final column as well. Cool. Yes, you can indeed. That comes up the last one. Sorry, we might have gone through these a bit fast, so I'm just going to copy and paste all the final ones into one thing. So ways of grabbing the final row. Yes. Function range. Same thing if you tail 5, you get the US. Yep. Yes, head and tail both take the same arguments, and you can tell if you do .tail and the right button. The signature here says n equals 5, return the last n rows. So in brackets, if I give it a number, it automatically fills n with that number. And so in this case, I could give it like 3, and it'll return n will equal 3, and it'll return the last 3 rows. This is actually shorthand for me going like this. It's the exact same thing. Being able to read these signatures is a skill which becomes very important in Python when you're trying to go through other people's code. Because understanding how other people's functions work is a skill, and is not always obvious how people intended for things to work. In any case, yeah, so there are a ton of different ways of grabbing the final row. And that concludes the challenge. So I guess we'll move on unless anybody has any questions. Sorry, does anyone have any questions? Awesome. Okay, so I guess moon stickers down. We'll continue. Oftentimes, beyond just going through individual row numbers, it's often important for us to know other aspects of our data, such as like how many rows or how many entries have a weight less than 5, for instance. So first off, I'm going to go over the .describe thing again. Remember, if you use .describe, it gives you the number of entries, the mean, the minimum, the standard deviation, the maximum, all of which can be really important summary statistics. For instance, I can tell that the data started collecting at around 1977 and stopped collecting at around 2002 for this data set. I can also see, if I scroll a bit to the right, that the minimum weight is actually 4, and the mean weight is 42. But let's say I'm interested in only the super small animals that were captured inside the Golan Desert. In order to do that, I'm going to use the index notation once again in order to grab just the weight column. I'm going to say, okay, less than 5. What this is going to do is it's going to give me this one-dimensional array, which is filled, so for each row, with either true or false, depending on whether or not the weight was actually less than 5. This is cool because you can store it in a variable, but it's also cool because we can use it as one of our subsetting methods. So using surveys and opening up our subset, I'm going to go ahead and put surveys for the weight less than 5. And we can see it has pulled out all of these records where the rate was exactly 4. Again, it's probably going to be exactly 4 because they were all the minimum was 4. And apparently they don't have decimal places, or at least they don't for the ones that are less than 4, just for these entries. Oh, sorry, yeah. So we took the surveys where the weight is less than 5, which gave us this giant Boolean array at the top, and we give that as one of our subset parameters, and we get only these rows where the weight was less than 5. I'm going to, sorry, this bottom thing is quite large, so I'm just going to write it inside of here. What about if we wanted to only grab a couple of columns? Luckily, we can still do .loc. We can still give it surveys where the weight is less than 5. And we can still just grab the weight in the species. Oh, sorry, this is getting slightly cut off. Maybe if I reduce the size slightly. Okay, this is just a temporary size reduction so that we can see everything that's on the screen right now. And we'll go over how to split things up in a second. But for now, we can see something rather interesting, which is there are only a couple of species for whom the weight goes this low. That's sort of to be expected. I believe the weight in here is like pounds, but I'm not. In any case, that's cool. You can see that there are exactly 17 entries that were like this. Sorry, I'll just leave that as normal, and then I'll copy and paste this code down here. Copy, paste, info, land. And we can see, yeah, there are exactly 17 entries for whom the weight goes this low. You might have also noticed that it kept the row numbers that it from the original data set, which is cool. And yeah, the species and the weight are all here. And 17 non-null objects, or sorry, rows, and the 2 columns that we've identified, which is cool. So what about if we wanted to subset on more than one thing at a time? Python implements Boolean logic, so we can do things like surveys.loc. I'm going to put this in circle brackets. Surveys where the taxa equal to rodent. And this and means Boolean and. So I've got one condition over here. So grab all the rows where the taxa is a rodent. And I'm going to grab all the rows where the sex is female. And this is getting really annoying, so I'm going to skip ahead in the lecture slightly. It is possible, if you're inside of a bracket, like this square bracket over here, it is possible to just split this up into different lines, and it makes it easier to tell what's going on. So I'm going to grab only the rows where the taxa is equal to rodent, and it was a female that was captured. And for sake of clarity, I'm just going to grab the 2 columns corresponding to the taxa and to the sex. And I'm only going to grab the first 5. So as you can see, or as you can imagine, this one gave me one Boolean array, which was either true for everything in surveys where the taxa was rodent, or false if it wasn't rodent. And then I ANDed that with another Boolean array where if the sex was female. And so by ANDing these 2 arrays together, I grab only the rows in surveys where it is both a rodent and female. Question, yes. Mm-hmm. Yes, but I think this is one of the faster ways of doing this. Like there are other ways of trying to grab only the rodents and then only the females, but this is by far one of the faster ways of doing it. Mostly because it's doing a lot of optimization in the back end that makes all of this extremely fast. Are there any other questions? Does everyone understand the? Oh yes, sorry. Right. And I think you'll find that if you use the AND here, it'll crash. This is because the AND symbol, this AND over here, is an element-wise AND. So because I've got 2 arrays, using the AND will AND each element in both Boolean arrays. If I just use the AND keyword, that evaluates the entire list as either a true thing or a false thing, which Python does, and it's useful for like if statements. But in this case, where we want to do this sort of element by element, that one has to be rodent, that one has to be female. Is the 2 of them together true? Then go ahead. Are there any other questions? Sorry, is that clear?
Yeah.
Any other questions? Awesome. So we'll continue going then. I've already gone through that. There is also a Boolean equivalent to the OR operator. So in this case, let's start off another loc. I'm going to enter a new line because it is really hard to. There we go. Let's see what I'm doing. Let's go with surveys where the species is a clarky. I've never heard of that species before. Or And the or symbol is that little bar thing. So R is or. If you're not certain where the bar is, for me, it is right above the enter key, and you have to hit shift in order to access it. It looks like a vertical bar. Surveys, where the species is leucophrys. Cool. In this case, I just want the species column. And you can see we have exactly 3 entries. One in the 10,000th row where it's a leucophrys, and one in the 24,000th row where it's a clarkie. I apologize if my pronunciation of these species is off. I have never run into these before. I do human biology. Is everyone clear on how the Boolean operators work here? Cool, because it's time for another challenge. So everyone put your blue stickies down, and I'm going to type out this next challenge. I sit down to do so. Challenge. Subset the survey data to include individuals collected before 1995 and retain only the columns year, sex, and weight. I guess I'll give everyone 10 minutes to do that. Yeah, yes, 10 or 5 minutes to do that. Feel free to talk to the person next to you. If you finish early, explain to them how your thing works. And if you run into any issues or have any questions, please put up your yellow sticky. Yeah, good luck. Okay. It looks like the majority of people have finished. So does anyone want to come up and type out their piece of code? Any volunteers? Raise your hand. Show me some excitement. You guys love data carpentry. Anybody? Otherwise, I'm just going to pick on someone random. Please, no volunteers? Okay, cool. So we're using the look command.
When did I do?
Remember your laptop.
Sure.
Also, you can just the way keyboard's a bit strange, I'm sure. Sure. Let's roll on. Okay. That's it.
Surveys, square bracket.
Yep.
Year.
Surveys for the year.
Smaller than 1995. Bracket year.
Yep.
Comma sex. Comma weight.
Awesome. And voila. Thank you very much. Cool. So as you can see, this gave us all of the columns, of which there are many, where the observation was collected prior to the year 1992. And we've grabbed the year column, the sex column, and the weight column. You might have noticed that there's a whole lot of missing data in here, and we will go over how to eliminate these bits of annoying missing data soon. For now, yeah, I'm going to split this up into 2 lines. You are correct. Voila. And we can see the years, yep, now we've got something from the year 1993 and from the year 1994. Cool. So without any further ado, let's continue moving forwards. So oftentimes when you're working with data, not everything that you need is there. Oftentimes you're going to have to do some sort of calculation yourself. In this case, I'm just going to take a look at the head again. I'm going to take a look at a couple of these weights again. You might have noticed it goes up to 204. This definitely isn't pounds. This is actually grams, and I was mistaken. And oftentimes we're going to need to do some calculation ourselves. In this case, the very first calculation that we'd like to do is to convert the weight column from grams to kilograms. In order to do this, all you have to do is surveys again, use the square brackets, and give it, instead of an existing column name, we're going to give it a new column name. We're going to call our new column name weight in kilograms. And set it equal to, remember whatever's on the left side of this equal sign will be assigned something. So we're assigning this new column the value of surveys for the weight, which is in grams, and we're going to divide that by 1,000. That doesn't type anything out by itself, so I'm going to grab the head of the temp and plan. You can see for the one non-missing number, the weight 218, now the weight is 0.218 inside of this new column that we've just created. Automatically add the new column. Make a new column. Whoa, new column. Yes. No. It only assigns it during this line. It's not like it won't like automatically update based on this expression. Everyone cool? Okay. So these NAs are starting to really annoy me, so I'm going to remove them. The command to do that is you put in your data frame and then dot drop NA. I'm just going to say remove annoying nans. Now, after I drop the NA, it's going to grab I'm going to use head to grab the first to the top 10. You might notice, firstly, the drop NA removed all rows where any one of the columns was NA. Secondly, if I were to, right after this, go surveys.head and equals 10, the NAs are back. The reason being is that I didn't actually assign this back to surveys. That being said, I'm not going to do that. So we'll keep the drop NA for now. The full row if any of the values were known. Dangerous. We will learn in a second how to fill the NAs with stuff. So, so we've got this piece of code here which drops the annoying nans, but I neglected to actually save that in surveys, which is why the next time around surveys.head, we still have the NAs here. Oftentimes, you don't actually want to remove all rows and censor them entirely. Sometimes you'll want to replace them with something logical. In this case, let's say the hind foot length first. I'm just going to grab the head so we can see what the first 10 things are, or the first 5 things are. See, 32, 31, nan, nan, nan. We can pretend that if we don't have the data, it's equal to some filler value. And in some cases, we might want to do something like fill it with the mean. To do that, I'm going to use fill_value is equal to surveys at hind foot underscore length, mean, grab the mean, and this will store it inside of the variable called fill value. Now it surveys hind foot underscore length. And I'm going to fill all the NA values with this new fill value that I just put inside of in the variable that I just filled in the first line. And then I'll grab the head of that. Sorry, like this?
Yeah, no, it's just that you were sticking totally.
Oh, sorry. Okay. You might have noticed, so I took the head and it had some of these NaN values, which are really annoying. I took the mean of all the hind foot lengths, and I'm like, okay, well, if I don't know what the hind foot length is, I'm just going to assume it's equal to the average. So I won't mess up my average statistic. And I can then take the surveys and take the hind foot lengths, and I can fill all the NA values using this new value that I've just calculated, which is apparently equal to 29.288. Again, because I haven't actually put surveys on the left side of an equal sign, surveys itself is actually unaltered for now. You can see, yeah, normally the hind foot length is still NaN in the actual surveys object. And in order to fill it, I would have to put surveys on the left-hand side of this equation. And I would have to remove the head as well. There is another method of dealing with NAs, and forget exactly what this method is called, but it's just like taking the previous entry and then carrying it forward, copying it forward. It might be just called like copy forward or something. But in any case, I'm going to copy and paste this. But instead of giving it a single value, I'm going to tell it, okay, fill NA, hit Shift Tab. You might notice usually it takes some value. You can also give it a method to change. And if I scroll down in this little help function over here, you can do something called backfilling or forward filling. That's what it's called, forward filling. And what that does is it carries the last observation forward. And so as you can see, for the hind foot lengths, it went 32, 31, and then the next three were NAs. And what we told it to do was carry the last observation forward. And if you go further down into the data set and you find more NAs, they'll just be filled with whatever was in the column. Yes. And we'll get to that in a second. Actually, it's the next section. Cool. Are there any other questions about drop NA or fill NA? Yes? No? Yes. Which values?
I don't know if there's some order to it. Otherwise, it just seems random. Like which row has
Yes, and in some cases, the randomness is desired. In machine learning, when you give it a giant data set and you're trying to figure out how to fill NAs, some people will just recommend that you use fill forward. Some people recommend that you use median. And it's really up to the scientist's discretion to figure out which one makes sense. But in some cases, the complete randomness of it prevents it from biasing around some particular value, which happened to be the mean, for instance. Are there any other questions? Cool, because we got another challenge coming up. Challenge. Create a new data frame. from these surveys contains only the species ID and hindfoot underscore length columns, and no NA values. Add a column to this new data frame. I'll just scroll down slightly. This new data frame called hindfoot underscore half, which contains values that are half the hindfoot underscore length values. Include only observations that have a value less than 30 in hindfoot underscore half. Final data frame should have 31,436 rows, 3 columns. Double check to make sure this is the case. Again, so blue sticky is down. Feel free to talk to the neighbor beside you and explain exactly how you managed to do it, especially if you finish early. Explaining it to other people is usually a good way of making sure that you fully understand all the concepts. And I'll give everyone another 10 minutes to complete this. Just to speed things up a bit and to make sure we're all on the same page, I'm just going to do question number 1, or just the first part for everyone. I'll just call this new underscore data underscore frame. I'm going to take it for the surveys data. I'm going to grab just the species underscore ID and the hindfoot underscore length columns. And I'm just going to drop the NAs. So this is question 1. I don't know how to stick everything all in one page. Actually, yeah. Can I get a volunteer to come up to answer question 2/3? 3 is not really a question, but somebody want to come up and share answer 2? Somebody who hasn't really raised their hand before and or done this. You want everyone? Yes. Sweet.
So which one? Flash.
You want to explain how you are solving this?
Okay. So I guess I can
Yeah.
just leave them. And then
Sorry. That was from.
anyways, sorry about that.
No problem. New is all good.
Mhm. Oops.
You're generating a new column called hindfoot half.
And then taking the original surveys hindfoot length column. and then just dividing that by 2.
Yep.
And then I checked it afterwards.
Yep. So I think problem. Thank you. Let's see, we've got 2 more rows, I think, which might just be due to oh, but it's still 2 more. Oh, haha, thank you. Okay, voila. Thank you very much. So the last step was to grab only the ones that have a value less than 30. And so the way to do that is to just use the loop command to grab all of the hindfoot hash lengths and then go for the ones that are less than 30. I'll give everyone a minute or so to copy that down. And then we'll go on to the super exciting split apply combine paradigm. I'll just give everyone a bit of time to copy that down. I'm also just gonna put that onto a different line. What it is. Actually, if I just there. All right, cool. So the next topic that we're going to cover is how we can split our data set into certain groups that we might be interested in. For example, if we wanted to find the average weight of for all of the different species that we found in our data set, or like the maximum for each species. And the way we do this is via something called the split apply combine paradigm. So I'm going to go into the GitHub notebook because it's a lot easier because it has this helpful diagram, sorry. But the basic idea is that we have in our input data set some key, which can correspond to anything, like the species, for instance. We've got some data that we want to perform some aggregation method over, such as summing them together or getting the average or something. So pretend, for instance, that we've got 3 species, A, B, and C, and we've got like a whole bunch of different weights, 1 through 6. The split apply combine paradigm allows us to split our input data set using something called the group by method into different smaller subsets of the data set. We apply some function to each of these split groups, and then we combine them in the end to get only, in this case, the sum of the weights. But we can easily apply any sort of function that we might be interested in. It could be like mean, it could be, in this case, I think what we're immediately going to do is compute the mean weight by the sex. So, actually, it's by the species. So, in order to do this, I'm going to use the group by command. So, let me just put a note here. Group by split combine apply paradigm. So, surveys dot group by, and if I can write that in the order, species. I want to combine it by species, or I want to apply it per species. And in this case, I'm interested in the weight. In this case, I want to apply to each individual species the mean function, which grabs the average. And so you can see there are quite a few species, some of which don't have a recorded weight. And there are a ton of different species here. you can see how this information might be really interesting and or useful. Question? Yep. Yes. So group by species, take the weight, calculate the mean. Yes. I don't know if there's an easy way to do that all in one command, but you can split that up into different grab it for each. Like, yeah, I can grab them in for the max. There are a ton of species here, so we might only be interested in a few of them. So I'm going to create a list of all the species that I'm really interested in. I call it species to keep. And I am particularly interested in Albigula, Horti, Flavus, and Torridus species. You might recognize this is the syntax to create a list. So I've created a list that has 4 different, actually I'll just type it up now. It has 4 different values, and each value corresponds to a species that I really want to keep in my output. In order to make use of this, I'm going to create a little subset of my list. So I'll call it surveys underscore sub equal to surveys outlook where. So I'm going to grab all the surveys where species, survey species, is in species to keep. Sure. So, how's that? Awesome. I'm going to split these up into different rows because it's getting really hard to see. And of course, because I captured the output, it doesn't actually show you anything. So let's just take the average weight per species, and we'll take our subset. I just took the subset of surveys where it was in the species that we wanted to keep. I'm going to use the group by command. Group it by species again. Take the weight again. Calculate the mean. And since I captured this into a variable, I just have to type the variable out at the end in order to get what the output is. And I'll scroll down slightly, but I'll go back up. I can now see the 4 different weights, the average weights for the 4 species that I'm actually interested in. You might have noticed that all I did was, the only unique part was like this subsetting thing over here to grab only the species. This line is almost the exact same as the giant group by that we had up there 2 commands ago. Just replacing surveys with our subset. So it's cool. We can chain these different techniques together in order to obtain exactly what we're interested in. So since I've got the average weight per the average weight per species here, just as before, since this is its own series, I can just grab the ones, like if I wanted to subset it even further, I can grab the Ordi and the Torridus, and it behaves just like the data frame would. So you might have noticed that so far we've only been printing out like species, or sorry, the weights with the species. Technically, since we've just grouped it by the species, that's all we get. But if we wanted to include multiple things, it's really easy to do that. So I'm going to go average weight per species and per sex is equal to surveys, our subset, because I don't want to deal with all of the species, and group it by. I'm going to give it a list. I'm going to put this on different lines so I can see what I'm doing. species and the text. So I'm giving group by this little list over here of the columns that I'm interested in. So I have to close that in order to do more functions on it. So I close the bracket. I'm now going to grab the weight from it, and I'm going to grab the mean of that weight. And I'm going to type it out because I captured that into a variable. Et voila. We can now see that I've grabbed for each species and for each sex of that species, the average wage. And it becomes even more apparent that for these, there isn't that much difference in between the males and the females, maybe a slight difference one way or the other, with the exception of the albigula species. I'm actually going to Google what an albigula is. Oh, it's a rat, food rat. Cool. Yes. So now we can see the power of giving multiple things to group by, and you could do this with any sort of combination of columns, and we could put in as many columns as we wanted to group by. Is everyone clear on how this is working so far? I guess you can put up your hand or yellow sticky if you're a bit confused. Otherwise, I'm just going to rush on forwards. Okay, I'm actually going to just, there we go. Now it's up and I can still play. We'll note that the type of this is actually sort of weird. Nope, never mind, it's just species. Okay, so just as before, I can grab only the species from that group by that I'm interested in. I can spell albigula. There we go. So it is still possible to perform subsets on this group by mean object. That being said, what if I'm not interested in entire rows? What if I'm only interested in certain values? So you might have noticed I'll take all of the albigula and all of the ordi. What if I wanted some more fine-tuned controls? What if I only wanted like female albigula and male ordi? The way to do that is, instead of giving it a list denoted by these square brackets as we've been doing so far, we instead give it tuples, which are denoted by the circle brackets. So first off, I'm going to use the look command as normal. Actually, I do still give it a list, but instead of just giving it strings, I'm going to give it a tuple. This is getting more and more complex to keep track of, but ordi female, but it would probably be easier if I split this up into multiple lines. So I'm going to grab just the female ordi and just the male albigula. Et voila. We have got just the things that we're interested in. So these tuples group together the column, the values that we're interested in. The female ordi, the male albigula. And in this manner, we don't have to see all of the albigula, all of the ordi every time. If we wanted, say, all the female, oh, yes, sorry. Lock is the good catch. .lock is more explicit. The brackets, oh, sorry. The brackets are shorthand notation. And in some cases, it'll fail. For instance, you can't choose both rows and columns using brackets. You have to use the .loc, as we saw all the way back up near the beginning of the lecture. And so when possible, I'd like to use the more explicit .loc. Even though you're right, we can just go without the .loc. Like that works. For to be super explicit with what I'm doing. So I'll write a small comment over here. Couples of so to select, what if we only wanted all the female observations? Well, we can use something called the cross-section command. Average, weight, species, sex, dot cross-section, XS, X is a cross, I get it. Female level equals sex. And that gives us all the, it sort of allotted the female column, but it's grabbed only the female examples inside of our data set. And last but not least, as with all data frames, we can see exactly what the names and the values are of the, in this case, so that this gives us the multi-index. It gives us the unique species over here and the unique sexes over here. So we've got all 4 levels of the species and the 2 levels of the sex. The labels here, so you might have noticed the labels here, 00112233, that's corresponding to how in just the raw average weight species sex, it's species 0 in the first line, species 0 in the second line, species 1, flavus, in the third line, and so on and so forth. And in some ways, indexing by this is extremely fast, or it becomes extremely fast to index things just by their numbers rather than asking Python to look up strings for you. Yes, sorry. Is there an order to it? I don't believe so. I think it determines that in, like, internally. Is there a pattern to how the indices here are determined? I think that's just like an implementation thing. Like it auto determines that. Unless it's like, you're right. Yeah, I mean, we could just look at that through here, or sorry, yeah. Is that what you were referring to? Right, yeah. Which would be the border over here inside of the raw CSV file we've been working for. Oh, actually, the mails come first. Not exactly certain. In any case, we can use the reset index in order to reset the indices such that instead of it being this strange series group by object, it treats it now once again like a data frame. That's why it's displayed in this particular format. And it's assigned its own like row names to it just based off the order. And so now all of these, the species, the sex, the weight, it's all stored as columns as well. So now we can do things like grab me the sex. Oh, it was a female, then a male, then a female, then a male. So this reset index basically converts it back to a data frame in simplistic terminology.
When you use this reset index, is it changing
The actual thing itself, no.
no.
So again, if I switch it back, it's still the same thing. In order to store it, I would have to use the equal sign again. Sorry, 1 second. So I'm just going to store it actually. Freeze for reset index. I'm going to store that inside of a variable, so now I can act on it as though it were a data frame again. And voila. All the species, the sex, the weights, and now I can use this average, weight, species, sex, reset index to suppose I wanted to grab only the female things. Sorry, I'm going to have to split this up into multiple lines again. And let's say I'm just going to store this just in case. Such that now when I output it, we can see we've got only the female weights, and I'm able to use this the easy shorthand bracket notation. It is, however, important to notice that this reset index command that we've been using can sometimes be extremely computationally expensive. So in some cases, it is not worth it to use it, and instead we would just use the cross-section command. Opposite operation to go from our data frame to the index is the set index command. I'm just going to shift tab. Set the data frame index using one or more existing columns. Great. Columns that I'm going to use are called species. They're spelled correctly on sex. Sorry, yeah. Further. This one. I'm gonna just both of them. So eating on forwards because we're running out of time. Yeah.
The first one is,
This one?
I mean, the set index is species is the one that becomes index. What's the second one?
The sex?
Yes.
It is the other index that's set.
Okay, so 2 indexes.
Yeah. So now you can subset it by species and sex. So the row indices are, yeah. Speeding up forwards, if everyone's finished copying that part down, is we can do multiple aggregations across our group data, which I guess is to your point if you wanted both the min and the different quartiles. So let's do groups surveys to our little subset still with the same 4 species. And I'm going to group by, once again, species and sex. Let's put this up in 2 lines because I can't see what I'm doing. And just as a really quick test to see that this is what we expect it to be, I'm going to grab the weight, and I'm going to take the mean of that. So we've got our 4 species, the 2 sexes per species that we've grouped together, and we've taken the mean for each of them. We have other aggregation methods, such as standard deviation, STD for standard deviation. Whoa, and you can see these mice appear to vary in weight quite a lot, or at least compared to these other ones. Keep in mind, this weight column is in grams, so it isn't actually that much of a change. Instead of using one of these pre-built methods, I guess we're still using a pre-built method, but another way of doing it is we'll take our weight and we'll use the aggregate command. Allows us to sort of specify, so instead of using the pre-built mean command, we can use .aggregate and tell it to use the pre-built mean command. Sorry, that was confusing. The reason why we use this .ag is that you can put anything inside of here. And if it's a valid function, it'll execute. So you don't have to rely on the pre-built commands in order to be able to do stuff. One of the cool things about this is that it also allows us to, I'm just going to copy and paste it, give it 2 aggregation commands. In this case, the mean and the standard deviation. Okay, voila. Now we can see it's got both of the things. In this case, it appears to be a data frame, and it's still based off these 2 indices, species and sex. We can also specify different commands to be done to different columns that we've aggregated together. So the way to do that is, I'm just going to write it out over here. Groups _ surveys. In this case, I'm going to grab 2 columns. Let's take the weight. Let's also take the hind foot length. I'm going to see the space I'm currently using. Ag is for aggregate. And I'm going to put this on different lines because I'm running out of space really quickly. I'm going to use a dictionary object represented by these curly braces, where it's just sort of like a key value pair. So I'll explain exactly how this works. We'll give it, let's say, weight, one of our columns. I'll put a colon here. And you know how in ag, I just put in like mean and STD? Well, I can do the same sort of thing over here. So I can do like, let's grab the sum of the weights. Then comma, so it knows for the column weight, just perform the sum. And for the column hind foot length, I'm going to perform 2 commands. And since I'm giving it more than one, we're going to have to give it another list. We're going to give it the min, we're going to give it the max. I am going to run this. And I'll scroll back up in a second, but you can see now for the weight, it has performed just the sum command. And for the hind foot length, it's given us both the minimum and the maximums. Let's give this some comments so that we know what we're doing. Do the mean and standard deviation on weight. And the weight for species. But also take the min and max hind foot length per species. It is just an open brace. So I'm going to scroll out slightly. Yep. Is it still legible from the back? I'm having problems keeping everything on the screen. Sorry, can you repeat that? Because I want 2 columns. Normally, you can't give it more than 1 column unless you use the double bracket. There are plenty of different aggregation methods located inside of pandas, besides the one that we've done so far. And we can find out all of them by using tab complete on the group data frame. That being said, there is a slight bug, which we have to work around in here. So the way we would, ideally, we would just do like groups underscore surveys and then tab. But let's say I'll create a temporary variable over here called find ag underscore methods is equal to groups underscore surveys, fire weights. Work it, I haven't actually executed it. Find underscore ag underscore methods dot tab, and we can see all of the different ends, some of which we've done so far. Some of these aren't. Standard deviation, some, size, etc. Unique. Moreover, the aggregate command, as I said, you can sort of give whatever to, and it'll do its best to execute what you gave it. So I'm going to import numpy as np. I think I did that all the way up above, but just in case I'm going to redo this, and I'm going to grab the numpy version of one of the functions and just give it to this aggregate command. NumPy.mean is one of the many functions inside NumPy to grab the mean of a bunch of a list. In this case, voila. There's no real difference in between this mean and the other mean that we calculated earlier, but you can sort of see the power of if I had other functions from NumPy, I could use any one of them. What is this? It was just a way for me of being able to use tab complete to like scroll through all the different methods that I can use on aggregate. Like first. So I could, for instance, instead of say min, I could put in first now, and it would execute that command. Okay, is everyone clear on that so far? XA. Yep. Sorry, I know this one's a bit of a large thing to copy. But that being said, it's time for another challenge. We're definitely going on before we do. So good, yeah. Again, I just use this dictionary structure in order to say I only want to run sum on weight, and I only want to run min and max on this. We all clear? So I'm going to put up the next challenge. Challenge. Use group by and ag. Find the mean, min, and max hind foot length for each species. What was the heaviest animal measured in each year? Turn the columns, year, genus, species, and weight. Hint. Click into the IDX max I'll give everyone 10 minutes to do that. So blue stickies down, yellow stickies up if you have a question, and blue stickies back up whenever you finish. And don't be afraid to just raise your hands and or talk to the person next to you. Perhaps you know something they don't, and perhaps they know something you don't. So we'll say at like 4:05. Has anyone finished the first part yet? Somebody who hasn't gone up yet want to share? You already put up your hand, so I've memorized who you are. Anyone want to volunteer? Please? Yes, go ahead. Oh, just the first one. Actually, what time is it? Yeah, just the first one. You want to explain what you're doing?
First group by species.
Yeah.
And then select. Yeah.
So group by the species. In the hindfoot line. Using the aggregate command, because we want to do multiple things with these. Yeah.
Oh.
Yeah, sorry. Thank you. So you can see, I'm just going to put this, move this so it's on multiple lines, and we've got the mean, the min, the max for all of our different species. For question number 2, the really tricky one, where you have to know how the index max method works. Remember to get hints on how things work, just hit the Shift tab. Oh, you have to, yeah. First. All right. Yeah. Yeah. As you might have noticed, the index max, after you do a group by, tells you the row number for each one of those years, if you grouped by the year or if you grouped by the species, the row index where it was the maximum. Look at these row indices. I'll give everyone another 4 minutes to crack at this. This one's pretty complicated. Anyone gotten it yet? Give you another tip. If you save this inside of the index max, this becomes pretty similar to one of the functions we covered at the beginning of the afternoon sessions lectures.
That is returning the row number.
Right. These are the row numbers where it was the maximum. Where in this case, it was where the weight was the maximum. I think in the interest of time and not going all the way until 5, I'll just type out the answer. So in this case, what were we interested in? Year, genus, species, and weight. Grab the year, the genus, species, weight. I look at our max index. You can see that for each particular year, it's dominated usually by one particular species and one particular genus of that species. Sorry, one particular genus and one particular species of that genus. The Neotoma albigula. But yeah, in one case, they caught something else that was larger than everything else in that year. So I'm going to flip this up. Everyone can see it. I'm just using the bracket notation to grab the 4 columns that we're most interested in. And then we use the .iloc command because we've got the row numbers that we want to grab. And we grab these row numbers by grouping by the year, taking the weight, and finding out where it was the maximum. Great. Once everyone copies this down, actually. The rows. Yeah. So I'm just writing a small comment to myself. This first line grabs the indices per year where the weight was max. And then I grab the rows corresponding to these indices. Well, I'm grabbing also just 4 columns, but yeah. So without any further ado, we're in our last stretch, final section. Once everyone has copied this down. Really? Which?
So that's for surveys, double bracket here, genus, feature free, five block.
So I'll give everyone like 1 more minute to copy this all down. I'll speed through the last section. Not speed through it. It's a really short section, promise. Okay. So without any further ado, we're going to be using the size command to summarize categorical data. So oftentimes it's really common when you're working with data to know the number of observations that either fulfilled some criteria or that were present in the first place. And the very useful command that we use for that is .size. But on its own, it's not actually that useful. We have to combine it with the group by function. Let's just group by the taxa and grab the size. What the size does is it tells you the number of elements in each particular group when you use the group by. If you don't have the group by, it'll just give you the size of your surveys, which isn't so useful. But in this case, it tells us, for instance, that we've recovered 34,247 different rodent samples and much fewer birds, rabbits, and reptiles back in this Grand Canyon. We can also use it when grouping on multiple variables. For instance, yeah, let's take the taxa again. I'm going to use the square brackets so that I can grab 2 columns, taxa and sex, and we'll just grab the size of that. And you can see that it's grabbed the taxa, and I guess for the other ones that didn't quite sex the animals, so we can't group by the sex. So we've only ever seen we've only classified the sex for the rodents, and so it's giving us 15,690 female rodents, 17,348 male rodents. If, however, we group by something that has a lot of entries by species, because we remember how many different species are on the sample, and then we take size, we get this really unintelligible giant list of different species. So it's not actually that useful if you have this much data, but we can do things to make this easier on us. we can do things like, I'm just going to edit the same values so I don't have to keep on scrolling up and down. Sort underscore values. Oh, and it sorts it in ascending order. Now we can tell that the most popular species is this Mariami, which is probably a rodent. But okay, I don't want to have to scroll all the way down to see what's happening. So let's go ascending is equal to false. I'm going to split this up in multiple lines. Remember, you don't have to split this up in multiple lines, but it makes it easier for me to show everything at once. Head, and let's just grab the first 5. So voila, we can now see the top 5 most numerous species that were caught by our researchers. Note that at each point in this step, all I'm doing is I'm chaining different methods together. I grabbed the size, I sorted the values, I took the top 5. We can split this up into a much more easier to understand way just by going surveys up there, dot group by, dot size, whoa. Dot sort values, sending equals false. Dot head 5. Now it's really easy to see from start to finish exactly what the steps are, instead of them being all in one horizontal line. Really easy to see what's going on. That being said, this whole size, sort values, and head is actually common enough that they've included a much simpler or a much easier shorthand for doing all of this. So I'm going to go on to the next one. Surveys. Actually, I wonder if I can show 2 at once. Yeah. And it's dot group by species. Dot size. Dot n largest. This dot n largest command combines this sort values and the head. The default is 5, but we'll just put that in to be super explicit. And voila, we can see we've got the exact same output from both of these lines. In order to get even more information about what's going on, I'm just going to copy and paste this code. And species. I'm going to grab a bunch of different columns now just to really all the details that I'm interested in. Species, taxa, genus. Grab me the size. Grab me the 5 largest. Bam. I can see that the largest group of species, taxa, and genus is the Mariami rodent, followed by the Penicillatus rodent, followed by a bunch of other different rodents. That's cool. Is everyone clear on how we got here? And you can follow the chain of commands? Because if so, any questions? No questions? You guessed it. We're on to our final challenge. First off, how many individuals caught in each plot type surveyed? Secondly, calculate the number of animals trapped per plot type for each year. Tracked only the year, but the combinations of year and plot type had the 3 highest number of observations. E.g., we might see that it's like the year 1998 and it was the control plot. I am going to actually just going to try and I could see both at once. I just captured the output of this into a variable so that it wouldn't output it. But yeah, actually, that's really not necessary. Anyhow, yeah, this is the final challenge. You have until, I guess, 4:30, which is when this workshop is supposed to finish. So nobody has their blue stickers up, but take your blue stickers down, yellow stickers up if you have any questions or any problems, or if you would like to flag down help to help you, and then blue stickers up when you finish the challenge. We'll just do challenge number 1 for now. So we go with surveys, we'll group by the plot type, and we'll grab the size. Yeah. We can see there are 5 different plot types, and the majority of them were just caught in a control. They also have the rodent enclosure, which explains why we have so many rodent samples. Cool. This is question 1. Somebody want to come up and share their solution to question number 2? Anybody with a blue sticker?
Oops.
We're grouping by 2 different variables this time. Plot type in here.
And then the size, and then also unmark list. And then I have maybe
Well, you had one more because you started off with another.
okay. Okay. There we go.
So thank you very much. As you can see, we've got the highest number of animals trapped were always in the control plot, but the absolute highest number was caught in 1997, followed by 2002, followed by 1982. With that, I think we're going to call it here because it's already 4:30. Yes, do you have a question? Splitting it into multiple lines. Otherwise, like if you try to split it into multiple lines without the bracket, it'll complain that it has no idea what you're talking about, this whole invalid syntax. But it understands it completely if you surround the entire thing with brackets. So any other questions? Is everyone clear? Clear as mud? Clear as mud. So I think this is going to conclude our lesson for today because we're out of time, unfortunately. But